Okay, in this example, I'm going to draw something that's a little more complicated than the hydrogen, and this is a homonuclear diatomic molecule, meaning it's made up of the same element. So we're going to look at the MO diagram for diatomic fluorine. So to begin, I have the electron configuration of fluorine written here. Remember, our energy is going to go from lowest, which is at the bottom of the page, to highest at the top of the page. So let's begin. So we're going to begin by drawing the atomic orbitals for fluorine. So we're going to put one here and one here. And we know our atomic orbitals to be 1s, 2s, and then 2p. And I'm going to draw the same over here. Like I said, once again, I'm drawing them at the same level because it's the same molecule, so all of their orbitals have equal energy. Now we can use these atomic orbitals to form the molecular orbitals. So once again, we know that 1s and a 1s are going to overlap, and we are going to form a sigma bond with the bonding and anti-bonding orbitals. So here's our sigma 1s and our sigma 1s star. It's a similar story for the 2s orbitals. They're going to overlap in the same way. And we're just going to, say sorry for the sloppy drawing, but these are going to overlap in the similar way. So this is going to be our sigma 2s, and this is going to be our sigma 2s star. Okay, so finally, we're going to have to overlap our 2p orbitals. So remember, p orbitals have 3 different lobes. It has px, py, and pz. And these are going to overlap differently to form either a sigma or a pi bond. So remember, the 2pz orbitals overlap head-on to form a sigma bond. So we're going to draw our sigma from the 2px. And of course, there's a corresponding anti-bonding orbital with that. Sorry. So this is going to be our sigma star 2px. So that takes care of our sigma orbitals. The other two, the py and the pz, are going to overlap sideways. And this is going to give us our pi orbitals. So we're going to create pi orbitals here. And there are 2 of them, remember. So there's the pi from the py, the 2py, and then there's a pi orbital from the 2pz. And they both have equal energy. And then, of course, there's the anti-bonding orbitals that correspond to them. So we're going to have pi of 2py star and pi of 2pz star. So this is our orbital diagram that we have to fill in. So I'm going to start by filling in the atomic orbitals using this electron configuration. So the 1s has 2, the 2s has 2, and the 2p has 5. So there's 1, 2, 3, 4, 5. And it's the same over here. So you can do this first if it's easier for you, but it doesn't really matter in a sense. Okay, so now we have to use this information to fill in our molecular orbitals. So in the case of the S1 overlaps, we have 4 electrons total in the 2 MOs, so we know that they're going to fill up. Remember, each molecular orbital is going to hold 2 electrons, and they're paired with opposite spins. That's why I'm drawing the arrows the way that I am. Similar story for the 2s, so we have the sigma 2s and the sigma star 2s. They also fill up from these 4 electrons. And then finally, we have the 2p orbitals with a total of 10 electrons, 5 from each. So our sigma 2px is going to be able to hold 2 of them. Our pi 2py and pi 2pz are each going to take 2, but I'm going to fill them in this way. So 1, 2, 3, 4. So that takes care of 6. We have 4 remaining, which are going to fill into the next level. So 1, 2, 3, 4. And this kind of rounds out our MO diagram for F2. So let's look at it a little bit. The first thing we're going to do is look at the bond order. Move this up a tad. Okay, so the bond order. Once again, the bond order is the number of bonding minus the number of anti-bonding. So all we really have to do is count here. So the number of bonding, there's 2 from the sigma 1s, so there's 2, 4, 6, 7, 8, 9, 10. And I just want to reiterate once again, these are coming from the sigma 1s, sigma 2s, sigma 2p, and the 2 bonding pi orbitals here. So that gives us a total of 10. Now we have to count the anti-bonding. So that's coming from this one, the sigma 1s star. So that's 2, 4, 6, 8. So it's coming from these 2 pi anti-bonding orbitals and these 2 sigma anti-bonding orbitals. And then of course all over 2 gives us a bond order of 1. What else can we look at? We can tell if this molecule is paramagnetic or diamagnetic. Once again, this has to do with whether we have paired or unpaired electrons. You can see by looking at these MOs that they're all paired. That indicates that our molecule's diamagnetic. And that means it won't interact in a magnetic field. And then finally, let's write the electron configuration. It's going to be a little long, but let's do it anyway. So we just begin like last time. We have sigma 1s 2, sigma 1s star 2, and I'm reading this straight from the MO diagram. So sigma 2s 2, sigma 2s star 2, sigma 2px 2, pi 2py 2, pi 2pz, excuse me, 2. Once again, these have the same energy, so it doesn't really matter what order you write them in. Similar story for the anti-bonding orbitals, but the bonding ones have to be lower than the anti-bonding. So this is pi 2py star, which has 2, and then finally pi 2pz star, which has the remaining 2. So this very long ugly thing here is the electron configuration. I'm going to leave it as an exercise for you guys to consider F2 plus and F2 minus. So consider their electron configurations, their orbital diagrams, figure out if they're paramagnetic or diamagnetic, and compare their stabilities, which you can do from the bond order. So specifically, what are the stabilities of these?